Hey everyone, welcome back to Brainstorm. In this video, we're going to go over the Level 3 2021 Probability Concepts paper. Now a disclaimer, I didn't actually take Level 3 statistics when I was at high school, so I do apologize if I do use some methods which you may not be familiar with. So let's get into it. So question 1, a music and dance festival sells two types of tickets, early bird and general admission tickets. For each ticket type, festival attendees under the age of 16 are able to buy a child ticket, otherwise they're classified as an adult. Early bird tickets need to be purchased before a particular date and they're cheaper than general admission tickets. For both early bird and general admission tickets, child tickets are cheaper than adult tickets. In 2021, 1/5 of the tickets sold were early bird. For those early bird tickets, 3/4 were adult tickets. For general admission tickets, 2/3 were adult tickets. So part A. The festival organizers predicted 10% of their ticket sales would be child early bird tickets. Were they correct in their prediction? So why don't we write down all the information that we know before we start part A. So we're going to need to know stuff about if the ticket is early bird or if it's GA, and we're also going to need to know if it's a child or adult ticket. So let's say let A be the probability, we'll say of an adult ticket, probability of an adult ticket. And because we're using probabilities, it can only be, in this situation, it can only be one or the other, right? It's either adult or child, early bird or general admission. And so what we'll do there is we'll use the complement, right? So we'll say let AC represent the probability of the child ticket, because it's the opposite, right? Also, we'll say let E be the probability of an early bird ticket, and then lastly, the complement of that would have to be general admission, right? Because you can only be early bird or you can only be general admission, right? General admission. Okay, so we've defined our sample space per se. So now what we'll do is we'll record all the probabilities that they've told us. So for 2021, 1/5 of tickets were early bird, so we know the probability of being early bird was 1/5. Given that there were early bird tickets, 3/4 were adults, right? So probability of being an adult, given that it was an early bird, was 3/4. And general admission tickets, 2/3 of those sold were adult tickets, right? So this is the same as the probability of A given general admission, and we've defined general admission as the complement of E or EC, that is equal to 2/3. Okay, so now we can actually approach A, knowing the probabilities that we do know. So the festival organizers predict that 10% would be child early bird tickets. So child early bird tickets, that tells us, if you think of it being like a comma there, this is an intersection, right? So we want to know the probability of being a child, which is the complement of being an adult, intersected with the probability of being an early bird ticket. So how do we work this out? Well, we actually know the probability of A given E. So if we work out the probability, so hopefully you know the conditional probability formula, which is if you have A given B, this is equal to the probability of A and B over the probability of B. And so if you want to work out the value of the intersection, it's the same as probability of A given B multiplied by the probability of B. Okay, so if we want to work out A, C, and E, we need to first find the complement of this and then apply this formula, right? So maybe we do it in a two-step process, right? So let's say that we want to find the probability of AC given E. This is the same as 1 minus 3/4, right? Because this is the complement of A given E. So this is the same as 4/4 minus 3/4, which is the same as 1/4. Now, applying the conditional probability formula down here, we know that that the probability of AC intersect E, which is what we actually wanted to calculate, right? Because we want to know child early bird tickets, not child given early bird tickets. this is going to be the same as multiplying 1/4 with the probability of having an early bird ticket, which is 1/5. So we've got 1/4 multiplied by 1/5. This is the same as 1/20. This is equal to 0.05. They told us that the probability should be 10%. So this is not equal to 0.1. Therefore, they made an incorrect prediction. Okay, part B. Calculate the overall proportion of tickets sold that were adult tickets. So we want to know what the probability of A is. Now, hopefully you might know that the probability of adults would have to be, in this situation, the probability of being an adult and you have a early bird ticket. And if you add that with the probability of being an adult being an adult and having a general admission ticket, if you sum these probabilities together, you'd get the overall probability of A. This is called the partition theorem. However, we only know given probabilities. And so using our conditional probability formula down here, we can actually rearrange this. This is the same as the probability of A given E multiplied by the probability of E added with the probability of A given the complement of E multiplied by the probability of the complement of E, or EC. So all we need to do now is just substitute in these probabilities. So do we know A given E? Yes, it's 3/4 multiplied by E, which is, or the probability of E, which is 1/5. This gets added with A given EC, which is 2/3, multiplied by EC, which is 1 minus the probability of E, or the complement of E, which is going to be the same as 4/5. So this is the same as 3/20 added with 8/15. So if we put that into a calculator, we should get 3/20 added with 8/15. So this is the same as 41/60. Part C, was it more likely for an adult ticket to be sold to an early bird ticket or a general admission ticket? So what do we want to know? We want to know probability that if you're an adult, given that you're an adult, was it more likely to get an early bird ticket or was it more likely to get a general admission ticket? So this is E given A. So early bird given that you're an adult, or general admission given that you're an adult. Remember that we defined general admission as the complement of E. So we're calling that EC. So let's do the first part. So let's call it part I. What's the probability of E given A? Well, the thing is, we only know the probability of A given E. And so we know the opposite of this, A given E. And so hopefully you guys know about Bayes' theorem. So what this means is we can represent this as the probability of A given E multiplied by the probability of E divided by the probability of A. Right? So what we can do is we can substitute in the values that we do know now. So what's the probability of A given E? It's 3/4. So 3/4 multiplied by 1/5, and that gets divided by the probability of A. Now the probability of A we calculated in part B to be 41/60. So if we fully calculate this, this should be 3/4 multiplied by 1/5 divided by 41/60. This gives me 9/41. Let's look at part 2 so we can make the comparison. So we're going to do the exact same thing. I think EC given A is the same thing as, what do we know? A given EC. So this is the same as the probability of A given EC multiplied by the probability of EC divided by the probability of A. Now this is equal to, what's A given EC? It's 2/3. So 2/3 multiplied by the complement of E being 4/5 divided by the probability of A, which is 41/60. And so if we put this into a calculator, what will we get? 2/3 times 4/5 divided by 41/60. This is the same as 32/41, right? And so which one was more likely? It had to be this second version here because the probability is naturally much higher, right? So the probability of EC given A was more likely. So remember, EC is our general admission ticket. So therefore, general admission ticket. Now, something I've just realized, I applied Bayes' theorem twice, but this is actually the complement of that. So if you just work this out and then just subtracted 941 over from 1, you would get 32 over 41, right? So that's a bit more of an efficient use of your time there. But therefore, GA ticket was more likely to be sold to an adult. Likely to be sold to an adult. Sold to an adult. Right, part D. In order to encourage people to buy their tickets early, organizers for 2022 decided to increase the price of some tickets, the GA tickets compared to early bird. In 2022, the relative proportions of adult and child tickets sold are expected to remain the same for each ticket type. If increasing the price of GA tickets reduces the proportion of GA tickets purchased overall to 1/2 of the original proportion, comment on the effect that this change has on the overall proportion of adult tickets that are sold as early bird type. So we want to compare the probability of, given that you're an adult, you buy an early bird ticket in 2021. In 2021, we want to compare that with the probability that you get an early bird ticket given that you're an adult in 2022. Now, what does the information tell us? We know that the relative proportions for each ticket type is going to remain the same. So what does that mean? It means the probability of A given E, the probability of A given EC, the probability of AC given EC, and the probability of AC given E remain the same. So we can reuse these probabilities. However, the probability of E and the probability of EC are going to change because the GA type reduces by 1/2 of the original probability. So the probability of general admission, that's the probability of EC, this is going to be 1/2 of what we originally calculated. So it was 4/5 before. So this is going to be 4 over 10, which is the same as 2/5. That now means the probability of E is also affected, and the probability of E is the complement of EC. That's going to be 1 minus 2/5. So 5 over 5 minus 2 over 5 should give me 3/5, right? And 3/5 plus 2/5 equal 1. So we know that we've done that correctly. Now we can go ahead and calculate what we want to calculate. So we want to find the probability of E given A. In 2021, what was the probability of E given A? It was 9 over 41. In 2022, we now need to recalculate this. So we use Bayes' theorem to do this. We will say, because we want to use Bayes' theorem because we know this probability up here. A given E multiplied by the probability of E divided by the probability of A. Now the problem here is our probability of A is not going to be the same as before because we've had to change the values of EC and E. So we have to use the partition theorem on the denominator. This is the same as A given E multiplied by the probability of E added with the probability of A given EC multiplied by the probability of EC. Now this is going to be A given E, which is same as before. It should be 3/4. So 3/4 multiplied by the probability of E, we've worked it out to be 3/5. Now 3/4 multiplied by 3/5 added with A given EC. A given EC is 2/3, and the probability of EC is 2/5. So this is equal to 9 over 20 all over 9 over 20 added with 4 over 15. Now this is equal to, so 9 over 20 divided by 9 over 20 added with 4 over 15. We get 27 over 43. Now this is equal to 0.6279, and 9 over 41 is the same as 0.2195. So what we can say is that the effect that this had is that more early bird tickets sold as early bird. Sold to adults, right? So what I'm trying to say is that given that you're an adult, you're more likely to buy an early bird ticket given compared to a general admission ticket. Okay, let's do part E. So an aim for the 2022 festival is to increase the proportion of child tickets that were early bird to 30%. Calculate the overall proportion of tickets that would need to be sold as early bird tickets in order to increase the proportion of all child tickets that were early bird type to 30%. Okay, so they've given us an unknown here. The unknown is overall proportion of early bird tickets. So we're going to call this P. So, proportion of all child tickets that were early bird. So given that you're a child, which was, what do you call it? AC. So the complement of an adult, that you buy an early bird ticket, we want this proportion to equal 0.3. Now, what is this formula? How can we expand this formula out? So, what we know, so we've called this probability P, but this can also be represented as overall proportion of tickets that would need to be sold as early bird. So this is the same as the probability of E, right? So I've also called this EB. This should be called E. Sorry. So what can we do? So we can reapply Bayes' theorem here. So we can say this is the probability of E given AC is the same as the probability of AC given E multiplied by the probability of E. See, the reason I wanted the probability of E is because we want to work this out, right? Divided by the probability of AC should be equal to 0.3. So what we're saying is 0.3 is equal to P of AC given E multiplied by our probability that we want to find out. In fact, let's change that to X because this looks kind of similar. So let's call this X over the probability of AC. Now, do we know these values? I think we would know AC given E, right? AC given E. Well, we know A given E is 3/4, so AC given E should be 1/4. So 0.3 is equal to 1/4 times X over the probability of AC. Now the probability of AC, we haven't calculated yet. We only know the probability of A, the new probability of A. So we had to use the partition theorem to do that. So let's use the partition theorem again to calculate the probability of AC. Or you can find the complement of A, it's up to you. But let's get some experience in, right? So probability of AC, this is the same as the probability of AC given E multiplied by the probability of E summed with the probability of AC given EC multiplied by the probability of EC. So let's go to a new line. 0.3 is equal to 1/4 multiplied by X over, what's the value of AC given E? We said that was 1/4 multiplied by X, because the value of PE was X, if you remember. Now, what's the probability of AC given EC? The probability of AC given EC, well, what's the probability of A given EC? That was 2/3. So the probability of AC given EC is 1 minus that. So 1 minus 2/3 should be 1/3. 1/3. Now we're multiplying this by EC. We don't actually know the probability of EC, but we do know the probability of E is X. So if we want to find the complement of that, it should just be 1 minus that probability, or 1 minus X, right? So this is the same as 1 minus X. So now we've got like a bit of algebra that we can rearrange for. 0.3 is equal to X over 4 over, let's try and simplify this, right? So remove this. 1/4 of X added with 1/3 minus 1/3 x. 0.3 is equal to x over 4 over, what's 1/4 minus 1/3? We get negative 1 over 12 x plus 1/3. If we rearrange this, we should get this over here is equal to x over 4. And as a result, what do we get? I feel like this cannot be correct. We'll find out later, eh? So 0.3 multiplied by negative 1 over 12, negative 0.025x, 0.3 times 1/3 is 0.1. This is equal to x over 4. So if we multiply the left-hand side by 4, we get 4. Negative 0.025x plus 0.1 is equal to x. Now, 4 times negative 0.025 gives me negative 0.1x plus 0.4 is equal to x. Let's bring this side back over. So let's continue our working here. So what's that? That's 1 plus 0.1. That should be 1.1x is equal to 0.4, and therefore x is equal to 0.4 over 1.1, which is 0.36363636. So that's our probability of x. Okay, let's do question 2. 3 different festivals are operating over the summer break. We've got Idle, Escapade, and Serendipity. Different performing groups or individuals can be seen at the different festivals. There are 37 acts performing across the 3 festivals. Idle offers 17 acts, Escapade offers 14 acts, and Serendipity offers 29 acts. 5 of the acts seen at Idle also perform at Escapade. 13 of the acts seen at Idle also perform at Serendipity. 3 acts can be seen at all 3 festivals. Calculate the proportion of acts at Idle that are unique to that festival. So before we do that, we can probably going to need to draw a Venn diagram, right? So let's draw our 3-way Venn diagram. So got my 3 circles, and let's use the information that they've told us to calculate what we want to know. So we know that 3 of the acts can be seen at all 3 festivals. So we know that this is going to be a 3 in here, and let's just call this, I, let's call this E, and let's call the bottom one S. So 5 of the acts at Idle also perform at Escapade, right? So we're saying that this, get my highlighter, this entire area here is 5, right? Because that can also include acts seen at Serendipity too. So if we subtract 5 from 3, we're going to get the unique ones that are, or the acts that are unique to I and E. So that's going to be 5 minus 3, which is 2. 13 of the acts at Idle also perform at Serendipity. So we're looking at this here. This entire value in here is 13. So if we subtract 3 from that, we should just be able to get this bit in here. So 13 minus 3 is 10. So finally, we've worked out all of this, so we can actually find the value inside of Idle. Now, Idle offers 17 acts. So if we subtract 17 from all the values in here, we should be able to find the acts unique to Idle, right? So that's going to be 17 minus 2 minus 3 minus 10, which is 2. So 2 in here. Now, from here on, we need to be able to, it's kind of like a puzzle, right? We kind of need to work out the other 2 pieces. So there's a few ways we can do it. Maybe we could use our intersection laws, but I think an easy thing to recognize is that this here, so all 3 of these intersecting bits here must subtract to give us 3, okay? So what that means is I'm saying 10 minus 2 minus this value in here, let's call this one x, it has to equal 3. Okay, 3 is our total intersection, right? So 10 minus 2 is 8 minus x is 3, and therefore 8 minus 3 is equal to x, so x is equal to 5. So we know that this intersection bit here is 5. Now that we know that, this is actually going to help us calculate the other values, right? So the value of S, serendipity, is 29. It's going to be 29 minus all this here, right? This is the unique serendipity x. So to calculate that, we subtract all these numbers from 29. So we're doing 29 minus 10 minus 3 minus 5. Serendipity has 11 unique x. And finally for E, escape aid has 14 x. The total number of unique x is 14 minus 2 minus 3 minus 5, which is 4. All right, and now we've completed our Venn diagram, we can actually go through and calculate all the necessary stuff. So the proportion of acts at idle, which are unique to that festival. So that's going to be unique acts is 2. And overall, there's 17 acts at idle. So that's 2 over 17. And that's it. All right, part B, or part 2. Which two festivals have the greatest probability of people seeing the same acts? So here we're interested in the intersection between two of the circles. So we'll look at the intersection here, we'll look at the intersection here, and we'll look at the intersection here. Okay, so how are we going to do this? So we're interested in the intersection between I and S, the intersection between I and S, intersection between S and E, and the intersection between I and E. Okay, and we're going to find the greatest probability, and that will be our answer. So the probability of I intersect S, this is what's the intersection here? The intersection between I and S is just going to be where the two circles collide, which is these values in here, right? So that's 10 plus 3, which is 13. So they're sharing 13 acts. Now what's the total number of acts? So we know that in total there's 37 acts performing across the festivals. So the intersection of I and S is 13 over 37. 13 over 37 is equal to 0.35135. The probability of S and E, we're just going to repeat it for pretty much the same process for the other two probabilities. So S and E, they have an intersection of 8 over 37, and the probability of I and E, they have an intersection of 2 and 3, which is 5 over 37. So what we can see is the largest probability is clearly I and S, right? Or the intersection between I and S. So which two festivals have the greatest probability of people seeing the same acts? Sorry, it is I is idle and serendipity, right? Serendipity. Part 3. A particular festival attendee can afford to attend only one festival. They wish to attend the festival that will give them the highest probability of seeing a unique act. Which festival should they choose? So in idle, how many unique acts can they see? Just 2, right? So that's 2 out of 37. At escape aid, the number of unique acts is 4. And at serendipity, the number of unique acts is 11. Okay, and therefore, if they want to see the festival with the highest probability of unique acts, it should be serendipity, because this will be the highest probability. So we'd say, therefore, serendipity. Part B. For people who attend only one festival, a model has been developed that predicts a festival a person will choose to attend based on various characteristics. To test a model, a group of 214 people were surveyed, and the actual festival chosen by each person was compared to the predicted festival from the model. Calculate the percentage of predictions that were correct. That is, the predicted festival was the same as the actual festival chosen for the person. Okay, so the probability of making a correct prediction. This is going to be, so given that you predicted idle, they actually went to idle. Given that you went to escape aid, they actually or given that you predicted escape aid, they went to escape aid, and given that you predicted serendipity, they actually went to serendipity. So this is going to be 80 plus 25 plus 5 over, I guess we'd want to know the total number of people, which is 214. So 80 plus 25 is 105, plus another 5 is 110 over 214. So what's 110 over 214? This gives me the probability of 0.514. Okay, so we're actually saying, well, they only predicted 51.4%. Oh, we actually want to calculate a percentage, so we should actually call this 51.4%. Right. Comment on the appropriateness of the model for predicting attendance at the different festivals. Support your answer with a calculation. Okay, interesting question, I guess. For predicting attendance at the festivals. So, I guess we can break down this calculation into kind of separate ones, right? So let's maybe say the probability of, given that you predict idle, you actually went to idle. So probability of, given that you predicted idle, you actually went to idle. Right, this is not really correct notation, but that's okay. So idle, so the probability that you predicted idle was, so these are the predictions, right? So 80 plus 7 plus 15, so if we go down the columns, 80 plus 7 plus 15, so we predicted 102 people would actually go to idle, but what we saw was 80 people went. So that's 80 over 102. That's 0.7843. So reasonably high accuracy for predicting idle. What about the other festivals? So if you predict escape aid, what's the probability that you actually went to escape aid? Well, we know that 15 actually went, and we predicted the sum of a column, which is 15 plus 25. 15 plus 25 plus 32, that's 72. 15 over 72, which is 0.2083. So we can actually see this probability is really low, right? So this wasn't really a good model for predicting escape aid. And let's finally do serendipity. So given that you predicted serendipity, what's the probability that they actually went? Well, only 2 people went. And this was out of 2 plus 33 plus 5, which was 40, 2 over 40. So this is a really low probability of 0.05, right? And so what does that mean for us? Was it actually 2? Oh, sorry, I've actually done the calculations wrong, because the people that actually went were 25 in escape aid and 5 in serendipity. So I better recalculate these final 2, right? So 25 and 5, right? So if I erase these probabilities, that's 25 over 72, which is 0.347. And this one in here, 5 over 40, should be 0.125. Okay? So what does this tell us? It means the model was reasonably appropriate, only for idle though. Only for idle. It has some, let's say, major issues with regards to accuracy for both escape aid and serendipity. So yeah, we'll say not a very good model. We gotta say as well, there's a low accuracy rate overall, right? That just comes from the fact that 51.4% we only calculate correctly, right? Now, part C, Patrick owns a food caravan and sells food and drinks. He purchases a bulk pack of 300 canned drinks. Cola is usually, so he gets cola, lemonade, and orange. Cola is usually the preferred flavor. So Patrick is pretty sad when he only gets 85 out of 300. Patrick thinks his bulk pack is a representative sample. He wonders if the proportion of cola drinks supplied is less than the advertised proportion. Okay, so you must think that they come 100, 100, 100. Okay, so 1/3 each. Discuss how carrying out a simulation would help Patrick consider whether his bulk pack could indicate the proportion of cola drinks supplied is less than 1/3. Describe what evidence Patrick would look for in a simulation. You don't need to design it. This is quite a stupid question. Okay, so right, so we'll say, I guess, a simulation allows us to get an understanding of what the population values look like, right? Because we never actually know the true population value, right, or population probability. If we did, then there would be no need for statistics, right? So we never actually fully know. But a simulation allows us to emulate that, given that if we increase the sample size if we increase the amount of like tests that we do, we kind of get a better and better indication, or a value which gets closer and closer to the population, right? So what I'm trying to say here is that if Patrick carries out a simulation, so what that would mean is he would buy a whole bunch of these bulk packs, carries out a simulation, we would be able to see Patrick carries out a simulation. He could, I guess, compare the observations over some period of time to his hypothesis. And his hypothesis is, I guess, a probability of having Coke or cola of 85 over 300, which is 0.2833. Okay, so he makes that comparison, right? He could compare the observations. So if the probability of cola is greater than 0.2833, then I guess we could say he got unlucky, right? Then he got an unrepresentative sample, and that's just due to the fact that there's variation in estimates, right? Right, so what we're saying is there's always going to be variation in different samples. Maybe not in estimates, we say variation in samples. Right, so there's always variation in different samples, right? But as we make more and more samples and we compare those over a long run, right? So maybe if we plot that, we'll see what the we'll get an idea of what the actual population value should be, right? If the probability of cola is less than or equal to 0.2833, then I guess we could say Patrick is onto something. Obviously, you probably want to write this. You'd probably want to write, I guess, then what he observed means that 85 cola drinks is representative. But anyway, let's do question 3. Festival tickets are sold either online or through a ticket office. The organizers have gathered data from the first 1,000 attendees to buy their tickets online. The data summarizes the age of festival attendees, either you're less than 25 or you're 25 and over. Their main motivation for attending, so it could be dancing, socializing, or other. 750 of the festival attendees are less than 25 years old. The main motivation of 510 of these is to dance. The remainder of these younger attendees are evenly split between those mainly interested in socializing or those mainly interested for other reasons. Okay, for those older than 25, 160 are interested in socializing. Of the remainder of the older attendees, 60% are mainly interested in dancing. Okay, so before we even do A, we just, generally, it's a good idea just to write down all the information we have. So, let's say the probability, let's create a random variable x, which is you're either greater than 25 or greater than equal to 25 or less than 25, right? So x is your age. So the probability that x is less than 25 is going to be 750 over 1,000. So what's that? 750 over 1,000. That's 0.75. That means that the probability that x is greater than or equal to 25 is going to be 0.25, right? Because it's the complement of that. Okay, what else do we know? The main motivation of 510 of these are, so we're looking at people less than 25. So given that you're less than 25, your main motivation to dance, so given that you're dancing, given that you're less than 25, is going to be 510 over 750, which is 0.68. What else do we know? The probability of socializing, given that you're less than 25, is going to be evenly split, right? So 750 minus 510 over 2 is 120, right? And the probability of other, given that you're less than 25, is going to be 120 over 752. So 120 over 750 should be 0.16. So if I change this to 0.16, 0.16, 0.16, and now we can look at it for over or equal to 25. So for those older than 25, 160 are mainly interested in socializing. So the probability of socializing, given that you're greater than or equal to 25, is 160 over 250, which is 0.64. The probability of dancing, given that you're greater than or equal to 25, so we're only looking at the remainder now, right? So 250 minus 160 is 90, and 0.6 of that is 54. So we're saying 54 out of 250, that's 0.216. Okay, that means that the probability of doing other, given that you're greater than or equal to 25, this is actually going to be equal to, either we can sum these probabilities up and find the complement, or we can actually do 40%, right? So 250 minus 160 multiplied by 0.4 gives us 36. So 36 over 250 should give me 0.144. And if we actually sum these, we should get 1. So that tells us that we've done it correct. So we know all the probabilities now, so we can just go ahead and do our calculations. Calculate the probability that the festival attendee is less than 25 years old and is mainly interested in socializing. Okay, so we want the probability that you are less than 25 and socializing. So S, I guess this would be kind of probability that, given that you're less than 25, given that you're less than 25, sorry, you want to be socializing. That's just the probability of 0.16. No, it's not, because this is an intersection. Sorry, don't know where my head is today. This is the probability of socializing, and x is less than 25. So are we going to say these events are independent? I don't know. We could also calculate this by saying the probability of s given x is less than 25 multiplied by the probability that x is less than 25. Now this is going to be 0.16 multiplied by 0.75. So 0.16 multiplied by 0.75, that gives us 0.12. So this is our answer. Part B. Festival organizers claim that it is at least twice as likely for younger participants to be mainly interested in dancing compared to older participants. So we're going to do the relative risk. So the probability of younger participants interested in dancing. So dancing given that you're less than 25 over the probability that you're dancing given that you're greater than or equal to 25. So dancing given that you're less than 25 is 0.68. That's over dancing given that you're greater than or equal to 25. That's 0.216. Now 0.68 divided by 0.216 gives us 3.148. So we're saying it's the younger participants are 3.148 times more likely to be interested in dancing compared to older participants. So at least twice as likely. Well, we know 3.148 is bigger than 2. Therefore, data supports the claim. Cool. Are the events festival attendee is less than 25 years old and festival attendee is mainly interested in dancing independent? Yeah, this is a good question. So how do we know if two things are independent? If two things are independent, that means that the probability of intersection is the same. Okay, let me explain this. So for independence, so for two events to be independent, what we're saying is that the probability of intersection, which is x less than 25 intersected with the probability of dancing, would have to equal the probability of x being less than 25 multiplied by the probability of dancing. Right, so if these things are equal, they are independent events. If they are not independent. So what's the probability of being less than 25 and dancing? This is the same as the probability of this is the same as the probability that of dancing given that you're less than 25 multiplied by the probability of being 25 or less than 25, sorry. Now this has to be equal to what we said on the right hand side. So less than 25 multiplied by the probability of dancing. So what's the probability of dancing given that you're less than 25? It's 0.68. Now this gets multiplied by x being less than 25, which is 0.75. This is equal to the probability that x is less than 25, which is, again, 0.75, multiplied by the total probability of dancing. Now, I don't think we know the total probability of dancing, but we can calculate it using the partition theorem, right? So if we look here, if we sum these two events here, this will give us the total probability of people that like to dance, I guess, or the probability that, yeah, that would just give us the overall probability of dancing, right? So what's that? 0.68 times 0.68 added with the probability of 0.216. So are these events going to be equal? I don't think so. So we get 0.51 on the left. And this is equal to 0.68 plus 0.216 multiplied by 0.75. I got 0.672 on the right hand side. So I don't know if that's, yeah, so what we're saying is that these are not equal. These are not equal. Oops. Therefore, they are not independent. Okay, interpret your answer in part 1 in terms of the relationship between the events festival, attendees less than 25, and festival. Right, so they just want us to write this in English. So what we're saying is that the events festival attendee less than 25 and attendee interested in dancing are dependent on one another. So what does that mean? It means that, I guess, the proportion of those whose main interest is dancing at the festival it actually depends on if you're less than 25 or greater than equal to 25. Depends on age. So x less than 25 or x greater than or equal to 25. Alright? And then finally, the last part, give 2 reasons why care should be taken when using this data to predict that a new ticket buyer purchasing buying a ticket will be less than 25 years old and mainly interested in dancing. So we have to look at how they sampled the data. So we know that tickets can be bought online or through a ticket office, but they only took 1,000 from the tickets online. Okay, so we say our first reason, so tickets can be purchased both online and at a ticket booth. Sample only considers the first 1,000 who bought tickets online. Right? So what we're saying here, in fact, let's not look at the 1,000 part now. We'll just consider those who bought tickets online, right? We'll say their behavior may differ from those who buy from a ticket booth, right? Buy from a ticket booth. So what we're saying is that this may not be a good model, right? The second thing is they only consider the first 1,000 buyers. We also know that the behavior from the first 1,000 buyers are probably going to be much different from the buyers that are, not in the first 1,000, right? The people that buy the tickets late, they might have completely different intentions, right? So the behavior of these people is likely much different from those who buy their tickets late. Okay, obviously you might want to include more information, but that's kind of the gist of it, right? Is that they haven't taken really a good representative sample. If you want to be able to make claims to a population, you have to have a representative sample, and this sample is not very representative, and so care needs to be taken when they use this data here. Okay, I think that's all I've got for today, so thank you so much for watching, and I'll see you in the next video. Cheers.